now.
Say yes.
Continue. Okay, we're
Hello,
live.
everybody, and good afternoon. Thank you for joining us today for our October podcast. I am Rizwana Khan, your guys' host, and we are doing a little bit something different this month. Our presenters wanted to do a live podcast, so this won't be a pre-recorded session, but it will still be posted on InfoZone. So for those attendees who are not able to attend, they will be able to view it in a few weeks on InfoZone. Again, if you have any questions, just like our other podcast, at any given time, please go ahead and enter them into the Q&A section. And Travis and Sandy will answer those at the end, as we do have time for that. Next slide, please. For those who are interested for AIA credits, this will be a 1 learning unit credit. So if you would like credit for this podcast today, please email me at rizwana.khan@kp.org. And now I'm going to go ahead and pass it on to our presenters, Travis English and Sandy Renshaw, who are doing the podcast on engineering, how to not save energy. Take it away, Travis and Sandy.
All right, thanks. Yeah, my name is Travis English. Sandy Renshaw is with me. So hopefully right away you get the irony of the title here. The title of this presentation is how to not save energy, and that's not what we want to do. In fact, in Kaiser, we have this mantra within National Facility Services that we've repeated for 10 years that talks about make every project an energy project. And the idea behind make every project an energy project is really that we do a lot of these capital projects that are almost once in a lifetime type of projects. A boiler project is a great example. If a boiler has been in service for 25 or 30 years, and then you do a boiler change out projects, and then that boiler sits in service for another 25 or 30 years, then that really is a once in a 50-year opportunity or a once in a 60-year opportunity to have a significant impact on the energy signature of a building. And so the idea within the National Facility Services that we've always held is that we need to take those opportunities as they come across our respective plates. So a little bit of background on some of the stuff we're going to show today. Beginning this year in 2023, my department, Facilities Planning and Design Engineering, started tracking the energy performance of projects. So per project, we're going in and we're doing some measurement and verification using the utility bills. So we look at pre-project energy and then we look at post-project energy. We run an M&V report and we file that report with the project. So in eBuilder, if anyone does Kaiser projects, you know that eBuilder is our system of record. So we file that M&V form in eBuilder under each cap number where the projects actually occur. And so we've started to accumulate a list of these. Most of the ones that we've done so far are the projects that were done in 2021 or 2022. So we have a year's worth of energy on that stuff. And we're starting to accommodate or build up a nice library of projects. This is the project and how much energy did it actually save. And so this is what the first half of that list kind of looks like. This is the list of projects where there is energy savings or where we found energy savings that we can associate to the pre-project period, post-project period. There's a savings in between there. And what's interesting about this is when you start to take a look at cost relative to energy savings, it's a scatter plot. It's kind of there's no correlation between the numbers. That's always important to point out because I think we all sort of have this knee-jerk reaction that if I want to do a project that saves a lot of energy, I would need to add cost to that project. And the actual numbers kind of show that that's radically untrue. The relationship between cost of the project and energy savings of the project can be really crazy. A couple examples. There's an example that's a second from the bottom. Richmond Hospital, we did a $3 million air handling project that saved all of 7,000 kBTUs of energy in a year's time. And then on the other side of the coin, so I think that's $400 per kBTU that we saved. So kind of ridiculously expensive. But on the other hand, you can look at, there's a nice one about 9 from the top. There's the Alpharetta DDC system. That was a $270,000 project that saved 1.4 million kBTUs of energy. So on that scale, that's less than 20 cents a kBTU. So it really is kind of a matter of getting smart scope into the projects and then executing that over the course of the project, not necessarily more money for more energy savings. Anyway, that's the first half of the list. Those are the projects that we found that did save energy. That's not what we're going to talk about today. What we're going to talk about today are some case studies off of this list. And this is the list of projects where we ran pre-project energy and post-project energy, and we found 0 energy savings. And you can see the size of the project ranges, right? It goes all the way from a $50,000 project up to a $23 million project. But these are all projects that really had that energy opportunity. So they're lighting projects, HVAC projects, boiler projects, controls projects. These are projects where we really could have seen energy savings or should have seen energy savings, and yet we're showing a 0 there. And so that's really what we're going to chat about today, how that actually happens. We're going to show you case studies off of those projects. Before we jump into the case studies, it's important to give you a little bit of primer about how hospitals use energy. Hospitals in particular, our medical office buildings are somewhat similar to this, but hospitals in particular. And that is that hospitals have a lot of what we call base energy use, so base thermal use or base electrical use, which is energy use that is independent of the weather. So you can kind of see on these charts, you have that blue rectangle down at the bottom. That's an amount of energy that gets used every month, regardless of whether it's winter or summer. On the left here is natural gas, and then on the right is electrical. And then, of course, you can see the orange, which is the up and down that we see that's associated with changes in weather. So on the natural gas one, that's associated with heating. And then on the electrical one, that's the up and down that's associated with cooling. Now, the way that we find that mathematically, the way that we find that is we actually run a linear regression or 2 linear regressions. We take the natural gas data and we run a linear regression against heating degree days, HDD. And then we take the electrical data and we run a linear regression against cooling degree days. And what we're looking for there is the y-intercept. That tells us where that blue rectangle goes. And then the part up above the y-intercept tells us what the weather-dependent usage is. So for this hospital that you've been seeing in this example, we're looking at base natural gas is 83% of the natural gas consumption. Base electrical consumption is 95% of the consumption. And so altogether, the base energy is about 90% of that hospital's use, 89% of the hospital use. Only 11% of the hospital's energy use is actually weather related. Now, of course, if you were savvy and you looked at this slide 2 slides ago, you'll notice that there's some orange pieces that dip below or dip into the blue rectangle, and that's natural, that's normal, that's because it's a linear regression, so it's never perfect, it's never a perfect model. There are some points that are above and below that line, but that's really just how we do the math. Anyway, as we show you pre-project and post-project energy, that is largely the way we're going to show you. So you'll see a bunch of slides that look something like this. So it'll be pre-project energy over on the left, and then post-project energy over on the right. And they will generally be these linear regression slides. And so just to walk you through what we're looking at on those regressions, the first thing we look at is, I went the wrong way. First thing we look at is the y-intercept. That's where it sets, that's the difference between the base and the weather-related energy. In this case, the y-intercept went up from the pre-project energy to the post-project energy. That means that the non-weather-related electrical use in the building went up from the pre-project period to the post-project period. The next thing that we'll actually look at is we'll look at the slope of the line. And in this case, the slope of the line went up, which means that the weather-related use, as the weather gets warmer, we're adding more and more units of energy per each unit of weather that goes up. So that's the second thing that we often look at. And the third thing that we look at is actually the accuracy of the model. So that's the R-squared of the linear regression model. In this case, the pre-project model is significantly better than the post-project model. The way we state that, by the way, the R-squared, so on the left here, we see an R-squared of 0.97. What that means is that the variance in cooling degree days can explain 90% of the variance in the electrical data, or 97% of the variance. That's quite good. A lot of the stuff we're going to see here is less than 80%. So to kind of jump to the end here, before we get into the case study, in order to make every project an energy project, what we need to do, number one, is identify the opportunities. So if this is an air handler project, let's look at what opportunities there are for energy savings within that air handler project. Second thing we need to do is goals and alignment. So set energy goals for the project. Use the building's historical energy use in order to determine what those energy goals would be, and then actually set numeric goals for the project. Next, during design, we need to look at options and look at options that matter. You'll see some examples in here where we're looking at options, but the options that we're looking at don't really matter. They're not that big a deal. And then, of course, during the design, we always want to look at the no cost and low cost system changes that would support improvement. These are the kinds of things that while you're there, you should be doing these things as part of the project. And they're often not huge lifts, so they don't affect the budget. It's just more of responsibility. Also during design, we need to set the goals for commissioning. So during design, there's a bunch of things that we need to sort of execute correctly: shutdown hours, turn down hours, equipment sizing, and then including enough metering to validate performance. That gets really important when we move over into commissioning. You'll see some negative case studies here that during commissioning, we need to validate the energy. If we set an energy goal for the project or we have energy aspirations, then we're going to want to validate that during commissioning. If we don't include the metering, very often, if we don't include the metering during design to validate the energy results, then we get to commissioning and we're blind. We can't see whether or not what we did worked or not. Okay, so that takes us to the first case study, which is this Elk Grove MOB boiler project. And as I mentioned already, boilers are really important. So for a lot of our buildings, natural gas is 25 up to 40 or 50% of our energy use. So heating is a major a major end use of energy in our portfolio. And of course, boilers are long-lasting items. They last for 20 years or 25 years. And so a boiler changeout project really is kind of a twice per century type of opportunity to have a significant impact on the energy signature of a building. So to kind of look at this project at an overview level, this is the project timeline and the project delivery schedule. The budget of the project was $544,000. We ultimately delivered the project at $414,000. Construction period was March to September. So not a terribly long construction period there. And then in this case, we had an OPR, and the OPR literally said replace in kind. So there's some references in there to meeting current energy standards, but that's kind of wishy-washy. In this particular project, there was no basis of design. So our engineer of record didn't do any basis of design. They didn't do any calculations. There was no commissioning. There was no looking at the system. There were no assessments. They did not look at historical energy data. They didn't even check the sizing of the boiler. They literally just replaced the boiler with the same size as the boiler that was already there. So any energy opportunities that were there, we sort of walked straight past those during the design phase. So this is the overall energy use at the facility. The way that we do these for M&V is we have that pre-project period we exclude the construction period. So that, whatever that is, 7 months sitting in there. In the middle, we're going to take that out of the numbers before we do the post-project energy. So we're comparing pre-project to post-project. And this is what that looks like. The weather-adjusted comparison, the usage is up by 20%. This is not terribly out of whack for, by the way, when the energy use goes up, then we call that a zero. We say the savings is zero. So we do have projects where in addition to not saving energy, we actually gain energy usage at the end of the project. This happens to be one of those. It's definitely zero energy savings. That's not terribly out of whack for a new piece of equipment. You know, if you kind of think about it, you have a 1990s boiler in place, and then it's chugging along, burning natural gas as well as it can, and then you put in a brand new 2020 boiler in its place, and it starts burning natural gas really, really well. And so we do see energy use go up. The efficiency doesn't seem to, the fact that it's a 97% efficient boiler on the nameplate or in the product catalog, we often don't see that come into play really at all. So this was our first case study, and these case studies will get sort of progressively better as we go. In this case study, we had no goals. We had no look at the historical utility data. We literally had no design, so there was no basis of design. There were no opportunities looked at during design, and there was no commissioning on this project in addition. So in addition to not having a design, we also didn't have a validation period with the project. So second case study here. This is at an Embarcadero medical office building, and this is replacement of some HVAC units. Significantly bigger project, both in terms of budget. This budget here was $6.1 million. We delivered the project at $5.9 million. Also, significantly longer construction schedule. You can see the construction schedule is quite long, representative of doing work on a hospital campus. Also, the design schedule is pretty significant here. The design schedule was a 14-month design schedule. So there actually was a good amount of time to dig in and do some homework and look at some of those opportunities during a 14-month design schedule. One of the big issues at this project that we're looking at, obviously in the rearview mirror, we're looking at these things as a Monday morning quarterback, right? This is not something that, make no mistake, my team and myself were involved in this project at the time. And so we're not saying that this was something that anybody did wrong or a mistake or an omission or anything like that. We're looking at this in the rearview mirror as a Monday morning quarterback and seeing what could have been rather than what happened. In this particular case, the Embarcadero MOB is part of the Fremont Hospital campus, and it's only about 11% of that Fremont Hospital campus. And the whole campus is metered together. So we have an electrical meter and a natural gas meter that goes into the whole campus, which means that if we had the whole campus energy, and let's say that we saved half of the energy at the Embarcadero MOB, well, that would really only have maybe a 5% impact on the overall energy at the meter at the Fremont Hospital campus. So whatever we were going to do with energy here at the Embarcadero MOB is going to get buried in the numbers, and that's pretty much exactly what we see. Long construction period here, but the numbers in the pre-project and the post-project. Obviously, we'll show another slide on this later, but there's not too much you can tell that's different between the two. Again, with this one, this was remove and replace OPR. And so that really is the starting point for a lot of this stuff. This OPR pretty literally says remove and replace the existing HVAC units and install new HVAC units. So there's a whole bunch that we could have done differently. We could have assessed the historical bill data. We could have looked at right sizing the equipment. We could have looked at some of those no cost and low cost opportunities within the building. But anyway, then we moved into design. The design here is a very generic, sort of straightforward basis of design and replace in kind type of sets of plans. So you can kind of see that paragraph right there is the narrative on the HVAC system. So it's not considering historical energy. There's not actually any load calculation. There's a checklist of things that we actually now ask teams to do that just didn't get looked at here. Where is the fan power relative to our fan power benchmarks? What's happening at this air handling unit, daytime versus nighttime? Are we actually shutting down at night? Are we setting back at night? Are there pressure resets that we can do within the ductwork or any of that? So those are all sort of opportunities that could have happened during a design narrative. It would have been a longer narrative than this, but when we did that, we really didn't take a look at it. And this design was, I think it was in 2017 that the design actually took place. So moving into commissioning, in this case, we had a significant commissioning effort. And you can kind of see that list there under 4.6 of the commissioning report. There's the acceptance criteria that we tested on the project. And you can see there's quite a number of them. We validated temperatures in all the rooms. We validated the relative humidity in all the rooms. We validated air handler space temperatures. We've validated the air handler static pressure. So we did a whole bunch of validation and a whole bunch of commissioning on this thing, which is a good thing. You can also look from the Monday morning quarterback perspective and say, well, none of that was energy related. So there's no reporting on fan power. There's no reporting on setbacks. There's no reporting on any pressure resets or anything like that. There's really no energy metrics at all. With one exception. The only thing that we could find in the commissioning report here retroactively is that we did test the economizer. So we do believe that at the Embarcadero MOB, we have an economizer that's working at the end of the project. But that's basically all we have in terms of energy benefit from this project. Again, pretty sizable project. To move into the results here are irrelevant. There's on the non-weather adjusted side, there's a 17% increase at the hospital. On the weather adjusted side, there's a 5% decrease at the hospital, but that's at the hospital. And the MOB is only 10% of the hospital, 11% of the hospital. So we have absolutely no evidence that any of that change had anything to do with this project. It could have to do with all sorts of different things that were happening on the hospital campus, not necessarily this. And so that kind of brings us to the second case study summary. Again, on this one, we did not have any energy goals. We didn't look at our historical utility data. We didn't really have any options that were considered. And then during our design execution, we sort of missed the opportunity to look at any of those low cost or no cost measures. And then during commissioning, we did a lot of commissioning, but the commissioning didn't include any actual energy validations. So I'm going to show another slide before we move to the next case study, and that is this one, which has come out of the overall slide. This has come out of the overall analysis here. The lesson that I want to communicate here is that commissioning is definitely not a silver bullet for energy savings. I think part of the reason that we do commissioning is we say, well, we do commissioning because if you commission a project, then the project will use less energy. This is that actual list that I showed you of projects that saved energy. The projects that saved energy, by the way, are the orange projects. And then on the same list, the projects in blue are the projects that did commissioning. So we had projects that did commissioning and didn't save any energy. And then, of course, we have the ones in the middle. This is to scale, by the way. So we have the ones in the middle. Those are the ones that we would like to see that did commissioning and they saved energy. So there is overlap there. And then we also have projects, by the way, that skipped commissioning. They just didn't do any commissioning, but they saved energy anyway. And we actually have a reasonable number of those. So I am not going to start disadvocating commissioning. I still think commissioning is a hugely important part of our quality assurance program. But I think it's important to communicate that commissioning is not, it's not an automatic silver bullet type of thing where if you do commissioning, you save energy. That's certainly not the case. So that being said, pass it on to Sandy for these next two case studies.
All right. You're a hard act to follow. Travis said a lot of the similar things that I'm going to say on these next two projects. I've got a boiler project and then an air handling unit project, and you will see kind of a similar theme. And can I go back?
Yeah.
Yeah, I just wanted to say one thing on this. Yes, we're not going to be advocating that, no, we don't need to do commissioning, but what we've also always said is it has to be a team effort. So you need the engineer and the commissioning agent working, as an integrated team. The commissioning agent's doing controls design now, and controls design greatly can impact the energy. I think in one of the first slides you showed that project that was a DDC project that was like
Right.
20 cents a square foot for energy savings.
Right.
Well, that was just simple sequence changes probably.
Yep.
So
yeah, and if you have energy goals that you can write into the project, then obviously you can commission them, and there's a great deal of value there. But
yep. And so this is the Meridian Medical Office Building Boiler Project. Pretty simple slide here. Like the other projects, this was a short 100-day design period. It's about a $500,000 project. Could have spent some money on retro commissioning. We could have bought smaller boilers. This is how we're kind of looking. Again, energy pre and then post. Obviously, we didn't include the construction period. And construction, I mean, this was a very quick, simple project. It's 4-month construction period. The OPR did have some good things in it. It did have reference to Title 24, which has certain energy requirements, but that's really more on boiler efficiency. There were commissioning requirements. There was a line about dual boiler variable primary system, which means, someone was really thinking about an energy efficient system. On the downside, there were no actual energy goals, no numeric goals. So this is in hindsight, and it was not done in design. This is, we are looking at this type of stuff now, but as you can see, there's an heating energy budget, and then there was a pre-project kind of linear regression analysis. And so we do have energy benchmarks now, and the building was well over those, like, what is that, 6.3 BTUs per square foot. Yeah. So, but the design team really didn't have any access to that data. And that's important, because had they had access to that, they could have done something about it, possibly go out to the zones. We could have been over pumping, overheating systems. And we did have a life cycle cost analysis, and we considered 4 different options. Probably could have bought boilers that were a little bit smaller. And as we said before, probably could have spent a little bit of money on retro commissioning.
Well, this is the case of, we did consider 4 different options here, but ultimately these are 4 different options with just kind of 5% variances in efficiency, which aren't really relevant to the overall problem at the building, right? The building was off by 200%, 300%. And so looking at 4 different boilers that are 5% off in efficiency is not really right, not the right tool for the job.
And it's probably too small on the slide, but some of these were condensing boiler options. Yeah. And with a condensing boiler option, if you have a traditional zone where you're, producing 180-degree water or even 160-degree water, you're not getting the benefit of the condensing portion of that. So you have to go out to the zones.
That's not just, and by the way, this is very normal. It is very normal in a boiler project or even an air handler project or a chiller project for us to look at 4 different model numbers, essentially, of boiler, air handler, and chiller. And that's what we call our life cycle cost analysis. I think the message here is that, we've been encouraging that for the last 10 years. But in retrospect, that's really not the.
And when this project, we probably weren't really pushing this as much.
Exactly, right.
Right. And so we did have some acceptance criteria, and they did include that in the commissioning plan. The diagram on the left is the acceptance criteria, and that was in the BOD and the specs. And what I will say is that's a copy of our template. It was not necessarily tailored to the project. So now we get to the commissioning part, and if you look at the screen on the right, all of the data points are above the line. So we clearly didn't make it. And the commissioning agent endorsed the project for, completion. And, in fairness to the commissioning agent, this is really more of a design process error and a system error. And I think what we've talked about before is we're not pointing fingers at any one person. It's really us as a group and the system and processes. And we're just trying to kind of give examples, and from that, we can improve our processes. And so this is the weather-adjusted energy comparison pre and post project. The variance is about 1%. So we replaced the boilers. We've got much more efficient boilers, but we're not really saving any energy, most likely because of turn down, and we didn't do anything in the zones. So the lessons learned, we really didn't have an energy goal here. The design team didn't look at the historical utility data, and as a result, the energy options they considered weren't really very meaningful. They didn't do any root cause assessment, and there were a number of things that were, suboptimal during design. And of course, commissioning reported success, which was probably not correct for the energy criteria. Did you want to add anything else on this?
No, that's it. Well, I think, the progression of these case studies, this is kind of the best project we've seen so far, right? It did have a design period. It did have a life cycle cost. It actually had an OPR that had at least a nod and a wink towards energy efficiency, and yet the results are what the results are, right?
Yep. And so this is our last case study. This is another air handling unit project. This was at the Ontario Medical Center. It was an air handling unit replacement that spent about $7 million on air handlers and an air-cooled chiller. Project had quite a long design time. It was a 14-month design period, and it had a year of construction. And part of that is this was an operating building, and I'm going to talk about this a little bit later. But it was it's an operating ambulatory surgery center. Probably operates 12 to 16 hours a day. And they tried to keep all the construction above the roof. They didn't want to, impact the facility. So the Ontario Ambulatory Surgery Center is part of the Ontario Medical Campus. And just like Travis said on the Embarcadero project, it's sometimes the energy use is at the cup, so it's hidden. But as you can see here, we discovered that they did have their own energy meter. This demonstrates the pre and post energy analysis, and obviously we didn't include the long construction period. And what we want to highlight too is energy was not analyzed by the design firm for the project. The OPR, like many of these we've seen, it's pretty simple. Remove and replace the existing air handling units and upgrade the chill water system. Nothing in the OPR regarding energy targets or goals. The basis of design addressed the need to lower the temperatures in the operating rooms, and to do this meant a standalone chiller had to be added so that you could lower the discharge temperature of the air handling units. The BOD did not have energy considerations, and also didn't address fan power, day-night scheduling, night setbacks, or any turndowns at the zone level. We didn't do anything at the zone level. We only looked at stuff above the roof.
I thought there was some design here for energy of the chiller, right? There was at least a kW per ton or something.
Once we started looking at the project, and as I said, I was involved in this project all the way through, and we had a really great team. We did get some acceptance criteria into the project, and okay. We've got that up on the screen here. And so what we did have was an air handling unit night setback, but it didn't go to the zone level. It was basically just
at the HU.
Yeah, like unoccupied settings at the operating room. An acceptance criteria for chiller turndown was included, but there was nothing in the sequence of operation that addressed that. It just ran 24/7.
Right. And
there was verification of an energy efficient cooling system. They set a target, and I think it was about 0.8 kW per ton. So that, we're thinking about it.
Right.
Nothing of turn down, fan power.
This is really important when you talk about an air handler, and the air handler can turn down, or the chiller can turn down, or the boiler can turn down. But if the demand out in the zones is constant, then congratulations, you just designed a turn down
Yeah,
not actually ever going to turn down.
we were still flowing, you
Yeah,
know,
exactly.
1,500 CFM in each
Exactly.
room.
Right.
So the first pass of commissioning did not validate any of the energy metrics. We got a report and they said, well, chiller power wasn't available. And they also said, well, facilities would not let the night setback scheme work. They locked it out. So we couldn't validate it by trending. And we discovered, you know, like I said, chiller power was unavailable. So we added a power meter and lo and behold, this is what we got. And as you can see, we're well above 0.8 kW per ton. And so we started looking at this and, you know, we got together, you know, we looked at this as a team and with an EER of 6.577, you can't achieve 0.8 kW per ton. The math actually comes out to 1.82 kW per ton.
This chart is also really interesting, just to, you know, to look at the sheer difference. You and I see charts that look like this all the time, and by this I mean they look really weird, as opposed to what design engineers. I was a design engineer for many years, and you see this number in a catalog that says, hey, this chiller works at, you know, this kW per ton, and then when you put it in service into a system, then we see some numbers that come out of that thing that are like this. They're all over the map.
It
right?
doesn't necessarily work. Yeah, and the chiller was running 24/7.
Yeah.
It was not turning down.
And it's a scatter plot.
Yeah. So we did revise the acceptance criteria. And as you can see, chiller turn down was removed because they were running at 24/7. The kW per ton was revised to 1.82, and so that passed. AHU night setback, the temperature setbacks, the commissioning agent did functionally test them and make sure that worked, but it was locked out, so
Right.
nothing was implemented. And so we can see, you know, still opportunities missed. We're kind of, you know, still hitting the nail on the head here, fan power and turn down at the zone level. And so this is the pre and post energy variance. As you can see, there's quite a bit more energy usage post project. And a lot of this actually is due to the fact that we added an air-cooled chiller instead of using house-chilled water. So of course we are going to use more energy, but we missed a lot of opportunities, and you know, we weren't turning that chiller down at all, or
Right.
any of the airflows.
Right.
And so, as we said before, we're not really targeting any one person or firm, you know, on the missed opportunities, you know, from facility assessments, design engineering effort, including commissioning. You know, most of the savings were missed. Planning and design, you know, me, so I take an equal share of this, and we were involved, you know, throughout the whole process, and we really had a great team. We had a good PM, good engineers, good commissioning agent, you know, people that cared about this, but you know, we were staying above the roof, so it really kind of tied our hands. And so, you know, I talked about it a little bit before. It's worth noting that we really weren't focusing on system assessments or energy targets, you know, when this design process was happening. And, you know, it probably would have been a little more difficult because, as you know, to get down into the zones of a, you know, operating building, sometimes it takes a lot of night and weekend work. But I mean, This is an ambulatory surgery center, so it does shut off at night. So we really could have done that. And so one final note, and that's a good final note, is the team is committed to energy savings on this, and we actually have formed a small group of us post-project, and we are working on implementing turn down at the zone level and, you know, turn down of the chiller, and we've got FAC Ops engaged and on board to work with us on that. So that's a good thing.
Yeah.
And I'm gonna turn it over to you for the conclusions.
Yeah. So this is where we'll jump out of our ironic presentation, right? So the conclusions here are, we're looking for how to not save energy, or we are actually looking to make every project an energy project. And we're showing these case studies just to be sort of, you know, cards face up on the table here. My team was involved in all of these projects, so we're just as guilty as anyone of this paradigm that we've been sort of practicing within the company, and that is just not just leaving opportunities on the table, but hopefully you can see that actually achieving energy savings in a project does require that you sort of set something up in the beginning, you identify an opportunity in the beginning, and then we really have to pull that all the way through to commissioning. So this slide I showed in the beginning, by the way, but it's under, we need to identify opportunities. Replacing kind is unlikely to produce any energy savings. It never does. So we want to set goals and alignments. We want to look at the historical utility data and make sure we're setting energy goals, numeric energy goals where possible, that come from that historic utility data. Make sure the results are measurable and say when and how we're going to measure them. During our design, we always want to be cognizant of what's happening in the systems, what's happening in the zones when you're doing the boiler, what's happening at the coil or at the valves and the coils when you're doing the chiller. We want to look at options that will actually get into those systems, look at system options in addition to those equipment options. Those system options are often the ones that can really move the needle. And then during design, there's we almost have at this point kind of a checklist of things to execute on during design. You know, what spaces are shutting down at night? What spaces could be shutting down at night? Those are low cost and very, no cost or very low cost programming only changes just to start taking zones down at night, terms down at night. Make sure that your design is very cognizant of the system temperatures and the differentials and the pressures and the flow rates. Work with what's actually there with the building, not what's on the old set of plans. And then, of course, for some of these projects, whether it's boilers or chillers, Sandy mentioned the chiller where we kind of we'll call it a failure, where we didn't map the kW point. Well, it's really important. If you're going to set a kW per ton goal, you got to map the kW point. If you're going to do a boiler efficiency goal, then you got to put the gas meter upstream of the boiler. So make sure in design we include enough metering or some logical way that we're going to come back and validate that performance later on. And then, of course, during commissioning, follow that through. If all of that is set up during design, then we'll have energy measures in the acceptance criteria. They should be relevant to the project, and then we will measure them and check them and validate them and make sure that we're actually getting that savings and logging it and putting it in the books. So just to show you some examples of kind of what we're doing now and what you'll see in the OPRs nowadays is that we are trying to put this numeric goal in the OPR, and very often that's my team that's setting a numeric goal and putting it in the OPR. It's usually we look at the historical data and kind of take a scientific wild ass guess about what we think the energy savings could be associated with the system. Better to put a number in there and then have the design team debate that number and sort of finalize that number during design than not to put a number there and just to miss entirely. So we're trying to do that. We're also in our OPRs, you'll see us talking about the system functionality validation and system options assessments. We've talked a lot about assessments in previous podcasts, and so that work really is relevant to trying to be able to get this stuff done. Again, I've mentioned it a couple times now. We literally have almost a checklist of stuff that we can look at during design that are energy measures, and this is where I want to emphasize. These are not things that add a ton of cost to the project, right? These are things where we want to look at the system that we're serving, look at the control points that we're serving, and see where we have stuff that we can do. Nobody's getting above ceilings or pulling permits or doing that kind of work. A lot of this is programming only changes. Check all the set points, check all the minimums on the VAV boxes, check the operating hours, non-operating hours, that sort of stuff. There's a lot of that we can do during almost all of our HVAC designs. And then, of course, commissioning, it wouldn't be an FP&D, Kaiser FP&D podcast if we didn't talk about database commissioning and validating all the measures. And of course, we have seen some, it's tough to say, but we have actually seen projects where our commissioning team is declaring success that's really doesn't meet the measures that we established. And so we've talked about that in some of our commissioning materials, that when we set an acceptance criteria and then don't meet the acceptance criteria, please don't write a commissioning report that kind of brushes that under the rug, that's time to raise the hand and have a larger conversation about the project goals and where the project actually wound up. And it's going to happen. That's going to happen on. It's going to continue to happen on projects, right? That's all we have really in terms of slides, right?
Yeah, we talked a lot about data. And so during the design phase, there is a lot of data available. You know, many of our buildings are on Clockworks, so there's historical data there, trending of the building automation system, you know, talking to Fac Ops, they've got a, you know, host of data, getting the utility data. Our team has access to all of that. So
Yeah.
we can get you any time period, and we can drill down into, you know, natural gas, electricity, and get any of those plots that you want.
Well, and those weather-related linear regression plots that you've seen throughout this slide deck, the natural gas versus heating degree days and electricity versus cooling degree days, our internal facilities metrics department has created a dashboard for us where we can literally, you just tell me the name of the building while we're on the phone, and I can send you a screenshot of that inside of 20 seconds.
Yeah.
So yeah,
That's
we
pretty
have
cool,
we have
yeah.
a lot of that data available to us. Yeah. So Rizwana, I don't know if you've had questions come in.
Yes, so we have some questions come in, and we also have some general statements that maybe, I don't know if you guys want to add, but I could go through them. So the first one, it looks like a general.
Camera here.
Okay, so the first one, it's a general statement or a comment. R2 value of 0.59 and even 0.87 doesn't confirm that there's a strong relationship with a high level of confidence between the variables and the function energy use.
We agree, yeah.
Okay.
A lot of our, yeah, I would love to find kind of a drop-off point for the R squared where we just say that, hey, listen, but by the way, it always terrifies me when we get a building that the statistically correct statement is that natural gas is uncorrelated to the weather. And that to me is as a mechanical engineer designing, you know, boiler systems, that's a horrifying statement to look at a building and we have something like Seattle.
It's a really flat curve.
It's a cold climate, and you say, well, the natural gas here is totally and completely unrelated to the weather. So that's a horrifying statement to me. But you're absolutely right. We have buildings where the R squared on that linear regression is less than 0.5, less than 0.6. And so to me, at some point, we're going to want to draw a line where we just say, listen, this building's not, the energy usage of this building is not weather related. I don't know where that is. And to be honest with you, when I see an R squared of 0.8, that's pretty freaking good in our portfolio. We don't have 0.97s and 0.95s. So we have a lot of 0.8s and 0.82s and things like that. Yeah.
Thank you. And here's another statement. Need supply temperature reset, volume reset when outside of occupied hours, and heat recovery off of steam boiler flue and chiller heat recovery. So this seems
those are all
like
good options.
Yeah, I don't know what that was referring to. Those are all good options that we can look at. Again, during design, those are ideas to look at during design.
Right. So here's a question. It seems like it might be broken down into a couple of questions. I'm going to read one, and then maybe you guys can answer that, and I can go to the next one. Did the presented regression analysis show a dependency of energy intensity on HDD only, no other variables?
So generally, when we run those regression analysis on the utility bill data, that's what we're doing. So we look at natural gas versus HDD, and then we look at electrical versus CDD versus cooling degree days. So natural gas versus heating degree days and electrical versus cooling degree days. So the idea there is that at the 0 point of heating degree days, those are summer months. Summer months have 0 heating degree days. And so the natural gas usage at those 0 heating degree days, that would be the y-intercept, which we kind of look at that as the base natural gas usage of the building, and then whatever happens during the months that have heating degree days is the regression. That's the actual slope of the line. Similar with electricity. With electricity, there's a little more baked into it because a 0 cooling degree day month, which is a winter month, that still has fans running, and it still has a certain amount of cooling running. So the cooling energy that's happening up in that regression part of the slope is truly kind of the weather-related marginal energy associated to those hotter months. If that makes sense.
Well, yeah, and using HDD and CDD also kind of helps normalize the data.
Correct. Yeah.
Because otherwise we could, compare 2021 to 22, and it could have been really hot, really cold versus not so hot, not so cold, and you think, hey, we did do much better with energy. But when you put it with the HDD analysis or CDD analysis, it kind of levels it out a little bit.
And it's one of those things where, HDD and CDD in a month is something that we get, by the way, from our utility data source. We use NG for utility data. And so every month it logs in HDD and CDD at that location in that month. So we get that in association with the energy data that we get. Would it be better if we had temperature and humidity at the site, hourly temperature and humidity at each site, and that we could run some really sophisticated data analytics tools? Yeah, it'd be a whole ton better. But for our 70 million square feet of buildings that are scattered across 500 buildings, we do have heating degree days and cooling degree days by month, and so we're using that. So it's a better than nothing thing, but obviously, what is it? The perfect is the enemy of the good.
All right. And the second part question to that is, did you have more variables that were crossed out later in the analysis as proven to not be a driving factor for energy use? It appears energy should have also vary as your occupancy schedule, et cetera, changes.
No, the answer is no.
Okay.
The one thing that I will mention there is that we actually wrote a little bit of an internal standard because when you take the energy data and convert it into a watts per square foot or a BTU per square foot, you do need the operating hours per month. And we don't actually know that. We don't actually survey all the facilities to find out what their operating hours per month are. So what we did is we have a little standard that says for hospitals, we do that based on 720 hours a month. For clinics, medical office buildings, and admin spaces, we do it based on 300 or 330.
And we consulted a much higher authority. We actually went to Google, and it tells you what for our MOBs, it gives you what the building operating hours are.
I think 300 hours a month actually.
320, 304, something like that.
A number around 300 hours a month comes out to roughly 5 days a week, and it's more than 12 hours a day. And so that's a number that we sort of use. That being said, when we look at that number and we see that one building is double on the electricity use, when you divide by 300 hours per month, that probably means that the fan is running 24/7 or running more than those hours per month. And so we're seeing a higher average. So we can get that out of that analysis a little bit.
Thank you. Next question. Can any opportunities missed in your case studies be addressed or mitigated after the fact?
I think Sandy's, the last project example is probably a good example. But I will say that's part of the sad part of this presentation. So to go back to maybe where I opened, when you think about a boiler project, a boiler lasts 25 years. You have in the year 2023, we're going to do a boiler change out project, and then whatever we do there is going to move forward for the next 25 years. So it's a once in 50-year opportunity to have a significant impact on the energy signature of the project. And the sad truth of the matter is, if you miss that opportunity in the year when you do that project, then no, there's no budget, there's no resources. Nobody's going to come along 2 years later and fix some of those issues. No, it's a little sad.
Next question. If there aren't any energy goals specified in the OPR, when is the appropriate time for the design team to develop those energy goals to include the project documents or to include in the project documents?
Well, I mean, the OPR is a living, breathing document, so you can always develop them and edit them back in. But certainly at the SD phase would be the time to kind of talk through what the goals would be for the project and get that baked into the design from the very beginning.
And by the way, I should say that's an internal job that we've taken on in 2023. So we try to look at every OPR that comes out in Kaiser. Every OPR that gets published to every service area in Kaiser, we try to look at those. And so starting not in the beginning of this year, but I think starting in Q1 of this year, we've been trying to do that. We've been trying to get that historical utility data into the hands of the design engineer, make that analysis available, and then also where possible, we've been trying to write that number directly into the OPR. So if you don't have a number in your OPR, then yeah, if you're in design, in schematic design, or design development, then yeah, please flag it to Sandy's attention, my attention, whoever your FP&D engineer is, and we'll want to work with you to get that done. I will say that there's a certain point, when you get to past design development, or you get into construction documents, or you've already ordered equipment, you've already nailed down your final estimates on the project, and there's a point where it's too late. You missed it. You missed the train, man, and it's already gone. And so we do have to be cognizant of that.
Thank you. Next question is, what if the building receiving the boiler replacement is planned to decommission in the next 10 years, but the boilers are failing? The boiler replacement cost needs to stay as low as possible, but support the building. Should you still be focused on energy savings?
I'll take a stab first, and I would say yes, but then you adjust the LCCA to 10 years and evaluate what's on the table. I mean, if we can show a payback within that time, then yes. I mean, obviously, if we're going to kill a building in 10 years, we probably wouldn't. I mean, we wouldn't go out and replace all the VAV boxes, but you could still maybe go out to the zones and tweak some of the airflows, maybe adjust water flow. Maybe there's a three-way. The common thing on boilers is you got three-way valves for recirc, and you're just continually circulating way too much water, over pumping it, and you can see that because you're going to have a low delta T. Right. And so some of that I would call that, wouldn't you call that low-hanging fruit to fix?
It is. Yeah, I think it's a great question, because it points us in this direction of when we talk about, what is the no cost or low cost things that you can do inside of a system, not a piece of equipment, but inside of a system. And the two that we recommend all the time are to have the engineer of record get all of the CFMs for the zones, right? So just gather all the CFMs for the zones and take a look at the max and take a look at the min. And then in a lot of cases, our minimums are too high. And so we're not doing very good VAV, where we have buildings that are running from 80% and then they drop down 10% and then back up to 100, and then, and so to just go through a building, and it's a spreadsheet exercise. You just plug in the areas and calculate some new minimums and then upload those to the zones, and do that reprogramming. Nobody goes above the ceiling. Nobody does any physical work in the building. You're just pushing new set points out to these zones. That's what we call a no cost or low cost. There's still labor associated with that, but you're not doing any real physical work. It's just it's programming and that sort of thing. And that's very, very common. The other one is the day and night. So we have a lot of zones that, I'm looking at this building in particular because I happen to suspect that it's the case that, I'm going to go home tonight. The lighting thing in here will go off. This will be an unoccupied zone, and the HVAC unit will still be running. And we have that just all over our portfolio. It's a chronic problem in our portfolio. And so to have the design engineer go through the zones, take a look at the software that's in the building, go through the zones and say, hey, listen, yeah, there's 15% of these zones that do legitimately need to run through the night, but 85% of these zones can be shut off at night, or they can be turned way down at night. That again, that nobody has to go above the ceiling and do any physical labor to achieve that. That is a no cost, low cost thing that we can do. So you can kind of see if you're doing a boiler change out and you take that time and effort to do those two changes on any of these projects that we showed you on the case studies, then make no mistake, you'll see a healthy energy savings as a result of that project, right? And so in the case of a leased building, where you don't want to spend extra money because we're not looking to increase the price of a project, but to go through those little bits of effort, you're not talking about breaking the budget of a project. You're talking about doing a little bit of work there and seeing a big return off.
Thank you, Travis and Sandy. We are out of time, and the rest of the questions and comments that that we weren't able to get to, I will forward them to Sandy and Travis so they can be addressed as needed. Again, thank you, Travis English and Sandy Renshaw, for a wonderful presentation on engineering, on how not to save energy. And again, please join us for next month's podcast. It is going to be held on Wednesday, November 15th. And the topic is going to be on our KP Brand Environments version 4. I hope you all can join us. Thank you again for joining us today. Have a wonderful afternoon. Bye now.